Hello everyone, I'm Sanqin Qu, a PhD student from Tongji University. Today I'm going to present our recent work on domain adaptation, upcycling models on the domain and category shift. As we know, deep neural networks often perform poorly when confronted with out-of-distribution data. To tackle this challenge, unsupervised domain adaptation (UDA) and especially recently proposed source-free domain adaptation (SFDA) have emerged as promising techniques. However, a significant limitation of existing methods lies in their reliance on the source and target domains sharing the same label space. In reality, target data often originates from diverse scenarios, making it unrealistic to rely on the assumption of a shared label space. To overcome this challenge, our paper investigates a novel and a realistic setting, source-free universal domain adaptation (SFUniDA). It enables model adaptation in the presence of both domain and category shift, providing a versatile solution for real-world applications. Here is the formal definition for the SFUniDA. We are provided with a pre-trained source model and unlabeled target domain data. The objective is to leverage the target domain data and the source model to acquire a target model. And the target model should accurately identify the known categories defined in the source model while effectively reject instances of unknown categories that are not encompassed by the source model. To achieve this, we introduce a simple yet highly effective technique called global and local clustering (GLC). GLC comprises two key components, global clustering and local clustering. The global clustering component is specially designed for pseudo labeling, where the local clustering component is introduced to mitigate the negative transfer. This page provides an overview of our GLC technique. Existing pseudo labeling strategies are typically designed for the conventional closed set scenario, raising a natural question: how can we achieve pseudo labeling when dealing with inconsistent label space? To address this challenge, we propose a novel one-vs-all clustering technique. This approach transforms the KV classification task into K-binary classification tasks. Specifically, for a given specified long category, our method aims to determine which instances belong to the category and which do not. In practice, we aggregate the top K sample instance to form the positive prototype, while the remaining instances undergo K-means clustering to construct negative prototypes. To enable adaptive clustering, we first estimate the number of categories presented in the target domain using the Sehoyster metric for assistance. Additionally, we introduce a strategy to filter out source private categories during the pseudo labeling process. While the one-vs-all clustering strategy effectively enables pseudo labeling for both known and unknown data samples, the presence of domain and category shift often results in a lot of misassigned pseudo labels. To address this challenge and mitigate negative transfer, we introduce a local KNN consensus strategy. The underlying insight behind is that data samples close to one another in the manifold space are likely to contain similar semantics. The optimization objective involves supervision from both global and local clustering components. During the inference stage, similar to existing methods, we utilize the normalized entropy as an uncertainty metric to distinguish between unknown and known data samples. We have evaluated our method on 4 benchmark datasets. The experiments were conducted across 3 different category shift scenarios, namely partition set domain adaptation (PDA), open set domain adaptation (OSDA), and open partition set domain adaptation (OPDA). To assess the performance of our approach in OSDA and OPDA scenarios, we employ the score as the evaluation metric. It's calculated as the harmonic mean of accuracies achieved for known and unknown categories. Here are the results in the OPDA setting. Our GLC shows remarkable performance, surpassing existing methods by a significant margin. For instance, on the VSDA benchmark, our GLC achieves an improvement of nearly 15% in terms of H-score compared to the SOTA methods. Here are the results in the OSDA setting. It's evident that our GLC continues to deliver SOTA performance. Notably, on the VSDA benchmark, GLC surpass the UMAD method by an impressive margin. Furthermore, the performance superiority of our method extends to the PDA setting as well. GLC achieves competitive performance compared to methods specially designed for PDA. This highlights the versatility of GLC in addressing category shift challenges across various scenarios. We have also conducted an ablation study to examine the components of GLC. The results validate the crucial role played by both components in achieving superior performance. In addition, we have verified the robustness of our method by conducting experiments that change the number of unknown categories contained in the target domain. The hyperparameter analysis demonstrates that GLC is stable and not sensitive to the hyperparameter selection. It's worth noting that most existing methods designed for category shift are not applicable to the vanilla closed-set domain adaptation setting. To further demonstrate the versatility of GLC, we have also conducted experiments in CLDA setting. The results indicate that GLC is not only effective in handling category shift, but also applicable to the vanilla setting. Furthermore, we have also validated the effectiveness of GLC in real-world applications. In summary, in this work, we present a novel approach for source-free universal domain adaptation, utilizing a genetic global and local clustering learning framework. Extensive experiments have demonstrated the effectiveness of our method. Thanks for your watching. Our code is already available at GitHub. If you have any other questions, please feel free to contact me.